So from this point on, it's recorded in the YouTube video because we're starting the hands-on demonstrations. Okay, you will use a new data set. This is the donation data set. It's different from the donor raw, although the case is the same. I mean, the scenario is similar, but you'll use the PV-A97, which is demonstrated in the PDF tutorials. So we'll use the same data set to get the same results. And you can download the data set from this week's folder, week 5, I think. You can download from week 5. Question?
No, I'm just stretching. Sorry.
Did the career fair turn out to be good? Yeah?
You're allowed to come
Great. Do you find the data set? Yeah. Okay, so start SAS, and then you can use the old project, or you can create a new project. The difference is, if you create a new project, you'll have to create a new library. That's the only extra step that you have to do. You can use the old project because you can have multiple data sources, and you can have multiple diagrams, and they are independent of each other. So you can lump everything into one project. That's fine. And you don't have to get to this point, but after you have downloaded the data set, after you have opened the SAS and have the project open, let me know. Roddy? Everything's wrong? Everything's okay?
Yeah, it's just there's a little bit of glare on the roof.
So you're looking at the data set? Oh, okay. Let's see.
make it rolling network just like that.
Just like that, yeah. Everything's good? Kenny?
It's just I'm at the library right now.
Oh.
I'll be caught up.
Fish? Same turn. Hmm?
The data file is the PVA9 as well.
Yeah, PVA 97. Everybody's there?
I seem to have more variables, the list is longer than this one.
Really? Any other has the same issue? You have more variables than I show here? So I may have 27. 28, 27.
When
Jenny?
we added our data source, could we just do basic or did we need to do?
Yeah, you can do basic.
Okay.
And then when you're on this page,
This is the variables page?
yeah, mostly that you need to change is to change the target B to have row target. Change the target D to rejected. ID will be specified ID by default. And that's it, I think. Most other things will be okay. And so after you specify sort the level column to better see, different kinds. And then you can compare with mine.
So it's kind of a little bit hard to see from here, just to make sure that target B is the one that's gonna be the target and
Yeah.
target D is the projected
Yes.
one?
And one thing, I think you need to change target B to binary. It's I think SAS will guess interval. Right? It is good.
Got it.
Great. Else?
No, I had trouble logging in, so I'm still trying to log in.
Oh, machine?
Yeah.
Oh.
Okay.
Sure. I mean, you still have more variables.
No, I think it was just the size of my room. And
Okay.
the sorting.
Yeah. Everything's good? Adi? Good. Alright, so for the sake of time, I'll do the data partition and then I'll help individually during the break. And then at this point, you don't have to specify decision process. So just go through the importing and have the data source ready, and then create a new diagram drag the data set over, and then you can skip this. That's fine. There are some missing values in it, but at this moment we're not bothered by that. The next one would be to modify. No, sorry, assess. Wait, not assess. Something.
Data position is in
Sample, right? Sample. So bring a data partition. Connect the dots, and then there's something that you have to specify. There are 3 segments. The twain is clear. We've been talking about twain. Validation is the partition that will be used more heavily than not, more heavily than the test set. It's used to look at the overall results, evaluation metrics for different models, and then use the metrics to select models and to eliminate overfitted models. So we want this to have at least more than the 30%. The test set is the one that's rarely used and that's most reserved, and we don't want to lose data points at this point. So we'll specify 0 here and with equal partition for the rest. Yes, 50, 50, and 0. And everything else seems good. After a run, take a look at the results. So this step may most likely may be a waste of time, but so you rarely spot any problem, but just in case there might be a problem, so you still want to look at it even briefly, even if very briefly. So what you're looking at here, you have a report of the data partition step. You can see number of total cases in the data set, in the overall training set. You can see the sizes of different partitions. You can confirm that the partition here, the mentality is to catch problems. Maybe you put in 5 instead of 50 in the partition, in the property. So here you're supposed to catch those problems. Most likely not. And SAS will equally, or try its best to equally allocate the data partition. So here, if it's equal, if it's even number of total points, then it will equally assign them to 2 partitions. So the number of cases need to be balanced. And then another thing, basically 2 things here. Another thing that's important here is you have the distribution of target levels underneath the 2 partitions. Now, I said that you want to examine the partitions to the extent that you don't look at the patterns and the noise is too much. So here, the only thing that you can see here is the overall distribution. That's considered the most basic information about the data set. That's the one critical piece of information, but very basic, is the overall distribution of the target. You want to make sure both segments, both partitions are comparable on this measure. For the entire data set, you have 50% level 0 for target B and 50% level 1. So half of them are donors, half of them are not donors. This critical information has to be maintained in every partition, regardless of the size of the partition. The percentage has to be comparable. So here, in the training set, it's very similar, although it's not not identical. It cannot be identical because of the numeric differences and randomnesses. But these are considered healthy, you know, and you want to maintain you don't want these two to be always the same because it depends on if they are the same in the original sample. You want to make sure that the first row is equal with the first row here, as with the first row there, the percentage. So look across the subsets and compare the percentage of a particular class. So for here, I didn't see any detect any problems, so we can move on. Okay, we'll take a 10-minute break. We'll come back. 43. Yeah, 43. Okay, let's get started. So, have you confirmed that the data partition is no problem? Great. I'll say you're up to progress.
Thank you.
Great. All right. So, then let's go directly to k-nearest neighbor. The name of the model is memory-based reasoning, MBR. So under model, MBR node, so drag it after the partition. Okay, there's some things to specify, and for the tutorial, you should use the other tutorial that says MBR, k-nearest neighbor MBR. It's only 4 pages. Oh no, we're going to use a different data set. Yeah, but I think, you know, I'll use this data set to illustrate the point. Basically, you know, you can accept the default algorithm to calculate the distance, and basically the only thing that you need to change is the k value, because that's an important parameter for the homework, and as for the illustration, use 4, k equal 4, and caveat of 2 caveats as for the MBR model node is that the number of neighbors specified here always allocate 1 for the case itself. So one of the nearest neighbors selected is always the point itself, and then which becomes a moot point. I don't know why. So if you need to identify 3 neighbors different from the focal point, you need to add 1 onto the number. So for homework, it asks for 3. It's better use 4 as the neighbors. You know. So that knowing the limits of the technologies is always one part of working with technology. So if you change to 4, you will see 3 different neighbors. And another caveat here for MBR model node is that whatever nominal binary variables, it will not be considered as part of the algorithm, right? So I think I forgot to do one step. Anyway, only the interval variables are included in the algorithm, and it's even implicit. It doesn't remind us. but just know that if you don't do anything else, then only the interval variables are included in the prediction. And it will become more clear in homework because there are a fewer number of inputs. So you'll notice that the marital status will not be considered if you follow the tutorial, and that's the only thing that's required for the purpose of this course, because MBR is just a lazy model, a lazy learner. It requires too much of a manual learning, which doesn't, it's a disadvantage from beginning. But before you connect, and another note, for the homework, do not partition. And for the homework, it's just to illustrate using the k-nearest neighbor model. Do not partition, otherwise you will see even fewer points. For the homework, there are only 10 points in the data set. If you partition, then the training subset, you have fewer points. Before you apply the k-nearest neighbor, it's important to normalize, right? So the transformation will take care of the normalize, as you know. It's under the modify. So almost always use transformation before MBR. And the purpose of transformation is to standardize the variables. And it's a simple step to do. Under the transformation, under the transform, for the default methods, keep everything as non and no, except for the interval input, and change it to one of the two methods that you can use to standardize the variable. The preferred one is the range. But really, it doesn't make much of a difference if you use range or standardize. Simply doing it is the right thing. And if you want to explore the results within this transformation node, then make sure you select the max to see all the points. Any other questions? So now, with the two nodes specified, you can run MBR. Razi?
Does it matter that transform is going to bin the variables?
Did you bin any variables?
No, but it says already has a value for a number of bins.
That's right. Probably have to disable it. Optional binning. Let me take a look at the exported data to see if there's any change made to the data that's unintended. So the variables are not binned by default, it seems like, but very good question.
You changed
Yeah.
something to max?
Yeah, under transformation, I changed the random. Change the first to random. This is just in case if you want to explore the transformation node to see the effect. If you want to plot anything inside, then it relates to the exploration function, and whenever you explore it, it draws a sample by default. if you want to look at the entire sample and make sure you select the max. Any other questions? Now, after you have run the MBR, it simply created in the back end. It calculates the distances based on all the inputs that are interval after range transformation, and then based on that, it selects the neighbors and include them in the 4 columns. So I set the number of neighbors as 4, right? So I have 4 more columns. One of the columns is the point itself. The way to look at the results of the neighbors is by look at the exported data. So highlight the MBR.
Did you change the method of MBR?
No, I didn't change it.
Because the tutorial we have online does put it to
Really?
scan. I don't know if
Really?
that's necessary.
Let's see. Did I forget? RD tree. That's right. Scan is the straightforward distance calculations. Did you use scan?
Yeah. I don't
Yeah.
know if that makes
Well, let's see if the difference is make a difference. So I use the default. Let's see. So you go to the exported data and look at the train. I will browse. Before I do that, okay. Okay, there are many columns, as you know, and there are many variables to start with, and additional columns are created on results of. Okay, so this is the training subset. So we know the original value for the target. So from target B means the original level, and into target B is the prediction based on the algorithm. Daniel?
Sorry, how did you get to that screen?
Highlight MBR and click the ellipse of the
Exported data.
exported data, yeah, and then go to training, go to train subset, and you have the confidence of predicting the level, each level, under this algorithm, and then the level with the higher confidence will become the actual prediction, right? And so confidence of predicting level 0 is 75%. That means the actual prediction is 0, and then 1 minus that confidence will become the residual, which is the error. And further down, you have 4 columns of nearest neighbor. And
Do you sort by anything, or because mine at the second row is different?
yeah, I kind of click the column header. So did I sort? I sorted by target B. From target B. So I probably should sort it by the ID number. Where's the ID? These are transformed. Yeah, it's dumb. Control number is a different number.
Observation number, right?
You're right. It should say ID, right? Did it say ID?
No, it doesn't. The label is observation.
Where's the observation?
After the nearest neighbor.
Right after?
Right
There you go.
there, observation.
Observation number.
Okay.
Number 1. Yeah, that works. Great, thanks. So for point number 1, one of the neighbor is number 1. So I guess the last column is the point itself. And the other 3 neighbors are actual nearest neighbors based on the standardized interval variables. And we have a few nominal variables like dem income or dem donor cat. These transformed variables don't have those nominal variables. So the nominal variables are not included in the calculation. Okay, so this is where you confirm the neighbors and to answer the question in homework. So 3 things are important for homework. Make sure you use k equal 4 instead of 3. Make sure you standardize the interval variables. And then know that the model don't use categorical variables. And that's it. And the rest of it you follow the tutorial. Any other questions?
Question.
Yeah.
So what we just did right now, did we standardize it?
Yes, in transform variables.
Okay.
Yeah. And in the table, when you browse the exported data, you see many columns created that start with transformed, right? So those are transformed variables.
And then you had said that we can answer the final question by looking at the train output from
Yeah.
MBR.
Make sure you don't partition the data set, the homework, and you can see all the 10 points, right? For point number 10, you can see the neighbors identifier, which points are the neighbors. Then you report the neighbors ID.
And it's okay for the binning, I think the default for the binning is 4.
So I think for interactive binning, it will create the binning that we did last time. But for transformation, it doesn't automatically bin. And the binning is just for exploration purposes. It's not actually binning it. Okay, let's switch gear to, let me pause the video. I think we need the data partition, but we don't need the transformations. And the things that I will demo is the decision tree PDF tutorial, beginning 3.2 on page 43. Everybody's ready? Right?
Okay, let me make sure the video is recording. Okay, so bring a decision tree to the right after the data partition. And before you do anything, don't even run it. And go into interactive. So you have a root node, and you're ready to begin to split the tree. So the first thing we'll do is split the node. So what's going on here?
Interactive is the property. Everybody's here? Yes? Okay. So what's going on here? For a split, SAS in the background, it does this. For every input variable that are not rejected, flashing. For every input variable that's not rejected, regardless of the type, SAS will apply a method to according to the level, according to the type of the variable. Let's say there's binary variable input, an input variable. That's a candidate decision rule variable, right? So SAS will do this. If it's a binary variable, it will use the binary two levels to split the training set as well as the validation. Right? It will split the data set into two subsets, and then, you know, it may be a good split, it may be a bad split, but it doesn't matter. SAS will calculate something based on the split. You sort of have a separation of the target, right? In let's say gender, for male group, subgroup, you have certain percentage of donors versus non-donors. In the female group, same thing. So you have 2 by 2 contingency separations of the cases. And then SAS can use that 2 by 2 to calculate the chi-square statistic. It basically calculates the correlation between gender and the separation of the donors versus non-donors, right? Chi-square is a way to quantify the relationship between categorical variables. Same thing as with the Pearson's correlation will quantify the correlation between two interval variables. Right? Same thing, but applied to different type of variables. So that's done easy for the binary. For a categorical variable that has more than 2 levels, SAS will do a blanket comparison. So for every possibility of split, let's say every time it splits into 2 branches, that's the decision tree model default setting. So split into 2 branches by default. It will take one of the levels, let's say income level, it will take the low and separate into a low segment and everything else into another segment, right? So it also creates a 2 by 2 and calculate a chi-square. And then starts over by separating by grouping the low versus medium income classes into one group, and the rest of it high income into the other segment, and calculate the chi-square. So that's the only possibilities. So another possibility is to group the low and high into one group, and the middle as a separate group, and calculates chi-square. So you have 3 chi-squares. SAS will compare it and choose the highest chi-square and to relate it to a specific variable here. So what you see here is a ranking of the variables in terms of chi-square. And every variable is listed once because the method of split with the highest chi-square is retained. Everything else is discarded. So what do you have here? You have thousands of decision comparisons in the back, which is selected, which is filtered by the best approach within each variable, and it ranks the variables, best method here, and displays the overall chi-square. So if you rank by not chi-square, log p, something similar, we're not bothered with the specifics. The overall logic is the same. The variable with the highest number of that statistic is gift count 36. So that gives you the best single split that separates the 2 groups. So for the interactive purpose, we'll choose, the first one is selected. You can rank them, you can choose a different, but the best one will be the one on the top. The next step will show you there should be edit rules. So you have the option to edit the rules under each variable. When you go into this rules window, it shows you the best split value of all the possible values. It doesn't show you the alternatives because it will be an infinite list of It will be ugly to look at. So it simply, chooses the best one for you, but you can change it whatever way you want. If you update it, the log p will be updated. If you change the value dramatically, it may end up not being the top, but you have the full freedom to do that. But the simplest way and the best way is to accept the default. And I've already applied it, so the split has happened. We have 2 branches and 2 decision rules. And then you can do more. Same thing, same logic. Every time the ranking and the variable and log p will be different. It depends on where you are.
So earlier the log p for the gift count 36 was like around 18-ish.
Yeah.
And now for the demographic median home value, it's like 3.4. Does that mean that it's less significant when it comes to comparing?
It can increase.
Okay.
So the log p is somewhat reflects how clean the cut is.
Oh,
As you
okay.
get to lower, more finer segments, the cut is
Okay.
cleaner. So you have even higher number, but those numbers are not available at first. You have to split it, to get there. The best case scenario is every endpoint, every leaf node has super high log p. So that's the clean cut after you have gone through something.
So its significance is only limited to that specific range.
Yeah, the ranking only makes sense within that content, within that segment. Right. Okay, I hope that makes sense. And then to make it easier, you can let it grow automatically by going with train node. It will assume that you will always choose the top one without changing the rules. So it will grow to a maximum. You can change the view to see the
entire tree.
is quite big because the data set is almost 10,000.
Would you click to just view?
No, you mean the
Yeah,
zoom in,
change
zoom
it.
out? Yeah, view to fit page. Everybody's here? You should get the same tree as I do.
It's hard to tell.
Yeah, it's hard to tell, yeah, but the shape of it, you have, so you can
What was the
compare.
variable you split with initially?
Gift count 36 months. Yeah, yeah.
Oh, and then there's like bold routes, and then there's like less.
Bold
like
routes.
regular.
Yeah, what are the colors represent?
Good question. Violet, let me clear your question first.
So like you see in the on your the second branch. So there's like two bold lines, and then for example that
These?
we have the gift count greater than or equal to 2.5, and then you see to your right
Mm-hmm.
the branch is bolder than the branch of
Right. Two very good questions. That's basically two things I need to highlight. One is the color. I think the color is more important. The color indicates how indicates the dominance. Indicates how clear the separation is. The darker the color, the more dramatic separation is. So that means efficiency. But in terms of training set. So this is the darkest. If you can see the percentage in it, the difference in terms of percentage is the biggest. So the confidence is higher, basically. The darker the color, the more the confidence in predicting that level. That makes sense? So you'll probably see 80-something percentage. So that's a high confidence of predicting the level, regardless of the level. But it's always predicting the majority of classification, right? Makes sense? If you see those, white ones, they are more evenly split. So they are low confidence. A second question, the branch width indicates the sides of the set of the branch. So as you go down, the sizes become smaller and the lines become thinner. So it's a quick way of visually telling where the points are going to in terms of the training set. But the two should be relatively consistent, right? So more points are going right to left, but not dramatic difference. But here, this cut is the majority of the points going to the right and further right, and down this point is more similar. Right, very fun.
Another question. So earlier in the second branch, when we do the split, we can see like there's a flip between donor versus non-donor in the two branch. For example, like the branch on your right
Yeah.
has a higher percentage of donor,
Yes.
and then vice versa for the left. But
You're comparing this one to that one, or
yeah,
these
yeah,
two?
that one to that one.
Right.
Now, if you go to that the fourth level down, that one, yes.
Yeah.
It has the same donor percentage comparing to its sister branch.
Yeah.
So that one and the white one, they kind of like have the same kind of. Oh, I'm sorry, I wrote that wrong one.
This is donor majority,
Yeah.
and that's non-donor majority. So it flipped.
The one in the middle, the median income region.
It's hard to see, really. Let me
Um,
make it bigger.
Okay, it's in the middle, and then you scroll down.
donor, and that branch is donor majority, donor majority, donor majority, and even this one donor majority.
Oh, so that means if it's branched from a donor majority, then
It doesn't have to be,
Okay.
but more likely.
More likely that it
More likely
will-
than not. It's not it's not impossible to have a flipped classification, just because of the subtle trends going on. Sometimes you can only identify a subgroup by first identifying a bigger group first. So how does it exactly work out depends on the data set, the context. But here you can clearly trace every point to where they are end up with and make the prediction. See, this branch is non-donor majority, but when you get to this
Yeah.
point, it's donor majority, it's flipped. But notice the number of cases are very small. It's a very small subset of the data set that shares many possible similarities, right? So, and the tree is limited by, you have to select the one rule and apply that rule to every data point at that point. So you cannot be fine-tuned to every point at every step. That becomes unfeasible, and the data, the model doesn't work. So there's this flipping and small subset problems. Overall, the concept works. Right?
How does the software know, like in some cases I see like it groups the missing values towards the greater?
That's the way you specify. So you can change it. Hold on. So by this point, the tree has been trained, so you can close it. Take some time to record the results, and then before you do anything, change anything, let's freeze it to not let the software change the tree that we just trained. So change that, and we still haven't run it, even though we have gone through that interactive and see all the results. So at this point you can run. The freeze tree option doesn't allow the software to make any changes, so that we can see the results of that exact tree. Razi, you have a question? Okay.
So we close the window first?
Yeah, that's fine. It's stored, but you freeze the tree first before you run it. Hami, there's an option under a splitting rule that asks you how to handle the missing values. So you have a few options here. It's grayed out now. You can choose to include on the lower branch or upper branch, or identify it as a unique branch. You have several options. So after you run it, go into the results. We'll take a look at overfitting graph. Now the tree didn't change. 1, 2, 3, 4, 5, 6 levels. 6 levels of depth. Wait, hold on. Go to the results. To see if the model has overfitted, do this. You're looking for the subtree plot.
subtree assessment plot. So click that. And the metric of comparing the model is selected as average error, average squared error. I'll talk about that in the slides. On the slides, we'll talk about that. If you change that, the lines will be different, but it's not a qualitative difference. For now, blue line is the training set. Red line is the validation set. Does that make sense? The x-axis is the number of leaves. That means those decision nodes that don't split out further. So at the bottom, how many leaf nodes are there? But we train a model that's here, that's indicated by the vertical line. It's 16 leaf nodes. But where are these smaller trees? We didn't grow them, but they somehow, somehow they exist and be compared. The vertical line is a frozen tree. It's a maximal tree. Has 16 leaves. Its error on the training set looks good, 0.23, 0.25, 0.24. But if you compare the two subsets, it's clearly overfitting. Right? It's overfitting beginning the fifth, or maybe the fourth or fifth subtree model. From that point on, it clearly goes north, and it's overfitting. Right? So you see that the theory has worked, and you can clearly see what models to select. A rule of thumb when you see the graph like that, and you have to select the best model, right? You select the best model, definitely not within the overfitting region, right? So from this point on, it clearly goes up. The error of validation data set goes up. So you definitely will not choose a model among these regions, and this plateau region of similar, validation set comparisons, you will select the simplest model of similar performances. It doesn't have to be bothered with the exact best performance, but sometimes you have to use intuition and select the easier models. I would choose 4, maybe, a model with 4 leaves. But with the model, we don't have a tree with 4 leaves. It's related to the pruning process, and it's already done in the process, even if we didn't ask for it. That's the standard decision tree algorithm in SAS. It grows the tree and prunes the tree automatically and compares all the best trees of each category. So let me quickly highlight some homework problems in case you want to get a head start on the homework. In the homework, it asks you to generate a table of all the decision rules. Daniel?
Just make sure you're talking about homework 4.
Yeah, homework 4 about decision trees. Let's do next Tuesday. So let's say that you have this tree. Just time up. Just one quick comment. So you have this tree. Suppose that this tree is the best one, even though it's not. For illustration, suppose this is the best tree. You want to report it, right? Obviously, you cannot put this tree there. It's too much information, and manager will look at you and think about, why am I even hiring you? So you want to present something that's more understandable. And all of these are the path is the path is of branching, so you can, you can describe them very intuitively. So you want to have something like that. Something like this table. This table summarizes what's going on in the decision tree model, right? If the 4 elements, if savings is median, then the prediction is good risk. There are 2 cases going into this branch, and the 2 of the 2 points are have the good risk classification, so confidence is 2 out of 2, 100%. That summarizes one decision path, decision rule. And then you have 4 more. 1, 2, 3, 4. So you have 4 rows. If you have 16 leaf nodes, you have 16 decision rules, completely from top to bottom. They may have different lengths, right? Depends on the path. But the table will summarize the tree very well. How do you get from the tree to the table? You obviously, one thing you can do is to read every box and transform the values into the table. That's cumbersome, kind of. So there's a good tool there. It doesn't get you exactly 1 step to the table, but that makes it much easier. So you want to be in the results window, and then you need to look at the model, view model, decision rules, note rules. It will give you something like that. It describes every leaf nodes, and then the complete path, and with complete information that you need for making a table. And from there, you need to extract the results for each node. These are the leaf nodes, completely leaf nodes. There's no middle step there. 16 leaf nodes here. And the mapping between these statistics with the with the table is illustrated in the slides. So you can go through the slides, you can find all the information. Right, for every leaf node, for the statistics, you have the if statements completely illustrated here. You simply have to copy paste, maybe. The result, you look at the majority class of the prediction, and you kind of have to know to interpret the meaning of the variable, because we're working with donation data set. The decision is donor, right? And then the majority prediction is level number 1, which means donor. Number of cases are illustrated by the number of observations in this node. And the confidence is the percentage reading for the label. And that's all you need. So do it for all the leaf nodes. The best tree will not have 16. The best tree will have 4, right? They only need 4. Or whatever the number is. Let's call it a day. If you have questions, let me know. I'll be here. Okay, class is dismissed.